Today, we are going to clear up one of the most commonly confused pairs in all of physics: power and energy. Let us start with a simple question. You have climbed up one floor of your college building. Now imagine climbing up 2 floors. Did you spend more energy? Absolutely yes. 2 times the height means 2 times the energy. For a person with a mass of 70 kilograms, climbing to the first floor at 3 meters requires 2,100 joules of energy. Climbing to the second floor at 6 meters requires 4,200 joules. Twice the height, twice the energy. And reaching the third floor costs 6,300 joules, exactly 3 times floor 1. Now here's the key question. Does it matter how fast you climb? For energy, the answer is no. Whether you walk up slowly in 30 seconds or run up in 10 seconds, the energy spent is exactly the same, 2,100 joules. But the power is completely different. The slow climber uses 70 watts. The fast runner uses 210 watts. Same work done, but 3 times more power. Power is simply the rate at which energy is used. Now, here is a beautiful analogy that will help you never confuse these two again. Think about motion. Speed tells you how fast you are moving at any instant. Displacement tells you the total distance covered. Power is exactly like speed. It tells you how fast energy is being delivered. Energy is exactly like displacement. It tells you the total work done. Rate versus total amount. That is the whole story. Remember, you can always get the same amount of work done, but how fast you do it determines how powerful you are.
Think about 2 fans in your room. Both run on electricity, but one is an old, heavy ceiling fan from the 1980s, and the other is a sleek modern fan with a brushless DC motor. Both move air, but the old fan draws about 300 watts, while the modern one draws only 35 watts. They both do the same job, but one does it far more efficiently. What is the difference? That difference is power. Power is the rate at which electrical energy is converted to useful work. 1 watt means 1 joule of energy is converted every single second. P equals W divided by T. The unit of power is the watt. 1 watt equals 1 joule per second.
Have you ever wondered why the unit of power is called the watt? It is named after James Watt, who lived from 1736 to 1819. Watt improved the steam engine so dramatically that it powered the entire Industrial Revolution. When he wanted to sell his engines to coal mine owners, he defined the horsepower based on the sustained output of a strong horse over a full working day. 1 horsepower is approximately 746 watts. Importantly, Watt was deliberately conservative. He set 1 horsepower at about 50% more than what an average horse could sustain. This gave customers a safety margin, and it helped sell his engines. The 3 power equations are the most important formulas in this course. First, P equals V times I. Power equals voltage multiplied by current. Using Ohm's law, V equals I times R, we derive 2 more forms. Substituting gives P equals I squared times R. Power goes up with the square of current, so doubling current quadruples power. Also, P equals V squared divided by R. All 3 give identical results. Use whichever form matches the 2 quantities you already know. Now we move from power to energy. Imagine a 100-watt light bulb. Leave it on for 2 hours instead of 1, and it uses exactly twice the energy. W equals P times T. Energy equals power multiplied by time.
The unit is the joule, but a joule is very small. Your 100-watt bulb burns through 100 joules every second. That is why engineers use the watt-hour and kilowatt-hour instead. Remember, power tells you the rate, energy tells you the total amount.
The joule is too small for everyday use. A 2-kilowatt air conditioner running 8 hours a day consumes 16,000 watt-hours. That is 57 million joules. So engineers defined the watt-hour, power in watts multiplied by time in hours. 1 watt-hour equals 3,600 joules. The kilowatt-hour, kWh, is 1,000 watt-hours. This is the unit on your electricity bill. 1 kilowatt-hour is the amount of energy a 100-watt bulb uses in 10 hours. That is 1 unit of electricity. The kilowatt-hour meter at the entry of your building records every unit your home consumes.
Now, we look at the power consumption and daily energy use of the most common household appliances. Every appliance in your home is rated in watts. This is its power rating, or how fast it consumes energy. The actual energy consumed depends on how long you run it each day. Let's go through the table. A ceiling fan rated between 60 and 80 watts running for about 10 hours a day consumes between 0.6 and 0.8 units of electricity. That's kilowatt hours per day. An LED tube light at just 18 to 20 watts used for 6 hours consumes barely 1/10 of a unit daily, making it one of the most efficient light sources available. A refrigerator of 180 to 200 liter capacity draws between 150 and 250 watts. But since it runs in cycles throughout the day, roughly 8 to 12 hours of active operation, it consumes 1.5 to 2 units daily. Your LED TV at 40 inches, watched for about 4 hours, consumes only 0.2 to 0.4 units, relatively low. A washing machine, though rated at 500 to 800 watts, is typically used for just 1 hour a day, so daily consumption is 0.5 to 0.8 units. Now notice the air conditioner, a 1.5-ton unit rated between 1,000 and 1,500 watts, run for 6 hours, consumes a massive 6 to 9 units per day. This is by far the largest consumer in the home. A geyser or water heater at 1,500 to 2,000 watts for just 1 hour still uses 1.5 to 2 units, comparable to a refrigerator running all day. Finally, a mixer grinder at 500 to 750 watts, used for just 30 minutes, consumes 0.25 to 0.4 units. The key takeaway here is simple. Wattage alone doesn't tell the full story. Usage hours determine actual consumption. High wattage appliances used briefly can consume less than low wattage ones used all day. Now we scale up the daily figures to calculate what each appliance consumes over a bi-monthly billing cycle, that is, 60 days. We use the maximum daily kilowatt-hour value from the previous slide for each appliance. Multiplying each appliance's maximum daily consumption by 60 gives us the bi-monthly figure. The ceiling fan, at 0.8 units per day, accumulates 48 units over 60 days, about 5.2% of total consumption. The LED tube light, at 0.1 units per day, contributes just 6 units, less than 1% of the total. The refrigerator, consuming 2 units daily, accounts for 120 units, nearly 13% of the bill. The LED TV and washing machine each contribute 24 and 48 units respectively, modest shares. But look at the air conditioner. At 9 units per day, it consumes 540 units over 60 days. That is 58.1% of the entire household energy bill. More than half your electricity cost comes from this single appliance. The geyser adds another 120 units, another 12.9%. Together, the air conditioner and geyser alone account for over 70% of bi-monthly energy consumption. The grand total across all appliances is 930 units for 60 days. This figure forms the basis of our electricity bill calculation in the next slide. Now we will discuss the actual electricity bill calculated by the Tamil Nadu Power Distribution Corporation, TNPDC, for 930 units consumed over the bimonthly period as of May 20th, 2026. The applicable tariff is LA1A, the domestic consumer tariff in Tamil Nadu. Let's walk through the bill. The total current charges computed before subsidies amount to 6,951 rupees and 50 paise. From this, a CC subsidy of 321 rupees and 50 paise is deducted, bringing the net current charges to 6,630 rupees. Then an additional CC new subsidy for the first 100 units, amounting to 495 rupees, is also deducted. This gives us the net amount payable of 6,135 rupees. Now let's understand how the 6,135 rupees was arrived at using the slab-wise table on the right. Tamil Nadu follows a progressive slab tariff system. The first 100 units are completely free, zero charge. Units 101 to 400, that's 300 units, are billed at 4 rupees and 70 paise per unit, totaling 1,410 rupees. Units 401 to 500 are charged at 6 rupees and 30 paise, adding 630 rupees. Units 501 to 600 attract 8 rupees and 40 paise per unit, another 840 rupees. Units 601 to 800, 200 units, at 9 rupees and 45 paise each, comes to 1,890 rupees. Finally, the remaining units from 801 to 930, that's 130 units, are billed at the highest rate of 10 rupees and 50 paise per unit, adding 1,365 rupees. Adding all slabs, 0 plus 1,410 rupees, plus 630, plus 840, plus 1,890, plus 1,365 equals 6,135 rupees, exactly matching the net amount payable. This clearly shows how a consumption-heavy appliance like the air conditioner pushes your total into the higher slabs, making energy efficiency critically important.
Let us cover the theoretical basis of system efficiency, grounded in the law of conservation of energy. The principle states energy input equals energy output plus the energy that is used, lost, or stored by the system. Dividing both sides of this equation by time t and applying the definition that power equals work divided by time, we get P sub I equals P sub O plus P sub used / lost / stored, expressed in watts. Here, P sub I is the power input, the total power supplied to the system from the source. P sub O is the power output, the useful power actually delivered by the system to perform the intended work. Efficiency as a percentage is then given eta % equals P sub O divided by P sub I multiplied by 100%. This tells us what fraction of the input power is converted into useful output. The remainder is lost internally. The right side of the slide gives us 4 key concepts to remember. First, what is P sub I? It is the total power supplied to the system from the source. Second, what is P sub O? It is the useful power delivered by the system to perform the intended work. Third, internal losses reduce efficiency. Power lost as heat, friction, or stored internally reduces eta. The greater the losses, the lower the efficiency. Fourth, ideal versus real systems. An ideal system has eta equal to 1, that is 100% efficiency. But real systems always have eta less than 1 due to unavoidable losses in motors, wiring, friction, and heat dissipation. Connecting this back to what we have studied, when your household consumes 930 units of electricity over a bimonthly period, that is the input energy. The useful work done, cooling the room, heating water, spinning the washing drum, is the output. The difference, lost as heat in compressors, motors, and wiring, represents the inefficiency of each appliance. A higher BEE, or Bureau of Energy Efficiency star rating, means a higher ADA. More of your input energy is converted to useful work, and less is wasted.
Let us discuss the BEE star rating system, the Bureau of Energy Efficiency's energy efficiency label for appliances. Star-labeled appliances carry BEE star ratings from 1 to 5, indicating how energy efficient the product is. Higher stars mean greater power savings. Energy labeling is mandatory for refrigerators, air conditioners, televisions, and many other household goods in India. Let's look at the 5 rating levels. 1 star, least efficient. These appliances offer approximately 10 to 15% savings compared to an unrated product. They are the cheapest to purchase but cost you the most in electricity over time. 2 stars, below average efficiency. These deliver around 20 to 30% savings, a modest improvement over the 1-star category. 3 stars, average efficiency with approximately 35 to 45% savings. This is the most commonly found rating in the market today, a reasonable balance between purchase price and running cost. 4 stars, efficient. These appliances offer 50 to 60% savings and are a popular choice for buyers who think long-term. 5 stars, most efficient. The highest rating delivering 65 to 75% savings in energy consumption. These carry the highest upfront cost but the lowest monthly electricity bills. Now, why do star ratings matter? There are 3 key reasons. First, lower electricity costs. A higher rated appliance consumes less power. This is especially important for high usage products like air conditioners and refrigerators that run for hours every day. For example, a 5-star AC saves approximately 3,000 to 5,000 rupees per year compared to a 3-star model. Second, environmental impact. Less energy consumed directly lowers your carbon footprint. Choosing a 5-star appliance is equivalent to planting trees and reducing carbon dioxide emissions year after year. Lower consumption equals a smaller carbon footprint. Third, cost versus long-term savings. 5-star appliances cost more initially than 3-star models, but they yield significantly larger savings on your monthly power bills over their lifespan. The break-even point is typically reached within just 2 to 3 years, after which the savings continue for the remaining life of the appliance.
This is the BEE label of a commercial refrigerator. It shows 3-star BEE energy rating on the 1 to 5-star scale. More stars equals more energy efficient. A 3-star fridge saves more electricity than a 1 or 2-star model, but a 5-star one saves even more. This rating directly translates to your electricity bill and carbon footprint.